Good morning, Chemistry 182. Due to popular demand, I am making a very short video on Bronsted Lowry theory. Now, Bronsted Lowry theory is essentially the updated version of acid-base theory as previously defined by Arrhenius. And in previous discussions, we've already talked about how Bronsted Lowry really is about the transference of a proton, which is essentially equivalent to a hydrogen ion. So when we say proton, we really mean a hydrogen ion. Now, we'll take a common acid. This is a nice strong acid for us to start with, hydrochloric. And what we're going to see is that when we dissolve it in water, we actually have a transference of proton occurring, okay? And what we see is that the proton, or the hydrogen, from our acidic entity is going to transfer over to our water. Now, when it does that, Cl is left simply on its own as an ionized entity, chloride, but H2O gains an extra hydrogen to become H3O, and that hydrogen is a positive ion, so we become a charged particle, which of course we know as hydronium. Now, this is what actually happens when you're looking at a container of HCl. Here's our beautiful stock container. perfectly rendered there. And so when you see HCl aqueous on the bottle, and usually some sort of concentration to go with it, so this is what we would see in Pixie's storeroom, then what you're actually observing is a container with this equilibrium present, okay? And in a strong acid almost fully dissociates, so the Ford's reaction is going to be favored, and we could demonstrate that by showing that reverse arrow as significantly smaller, okay? So what does this mean in terms of Bronsted Lowry designation? Well, Bronsted Lowry definitions of acids and bases are such that if something donates a proton or a hydrogen, then that becomes our Bronsted Lowry acid, okay? If something can accept a hydrogen, then that becomes our Bronsted Lowry base. Then what happens is that, as I say, we reach this equilibrium, and mostly with a strong acid in the forwards direction. Then we have these entities here. Now, how do we label these guys according to Bronsted Lowry definition? Well, what we do is we pretend that we are going to shift the equilibrium back the other way. We're going to favor the reverse reaction, and we're going to do that by modifying something in the reaction itself. So we're going to say, for example, boil off some of the water, or maybe that's not a great example. Maybe instead we should remove some hydrochloric acid, okay, in some way. So if we do that, whatever shift we have to do in order to make sure that the reaction favors the reverse process, then what we are going to observe is that the reaction between these, in order to reestablish our initial reactants, is going to involve hydrogen ion transfer as well. So in this case, the only thing that can give a hydrogen is hydronium, and it will donate back to the chloride in order to reform hydrogen chloride, okay, or hydrochloric acid. So in this case, this is an acid. This is acting as an acid in the reverse process, and this is accepting the hydrogen, so it's acting as the base in the reverse process. Because it's the reverse process, we're going to call these the conjugates, conjugate acid and the conjugate base. And the last thing to do is to link together the entities as they are separated by simply one hydrogen. So what does that mean? Well, HCl and Cl- are the same entity with the exception of one hydrogen. And H2O and H3O plus are the same entity with the exception of one hydrogen. So I link together those guys there. So the black arrows on the bottom here represent Bronsted Lowry conjugate acid-base pairs. Okay, So this is connecting the two pairs, the two entities that are separated by simply one hydrogen. Okay, so that's an acid reaction. Let's quickly look at a base reaction. Now, a base reaction can be any hydrogen polyatomic ion with a negative charge, or it could be something more simple, like let's take, for example, H2O, and in it we're going to dissolve some carbonate ion. Now, of course, carbonate, we can't just take a scoop of carbonate ion and put it in there. What we would do instead is use some sort of spectator ion like sodium carbonate, and we would use that to get it in, and then sodium wouldn't be part of the reaction at all. It would be a spectator ion just sitting there doing nothing, okay, in our container. So let's have a look at this reaction here. What we're going to see is that one of these two things can donate a hydrogen, and it's probably going to be the only thing in this particular case that has hydrogen. Now, I've written water as H2O. Sometimes it's a little easier to visualize this as HOH. So just remember that H2O and HOH are the same thing, and use whichever one your brain happens to like better on that particular day. So here we have HOH and CO3 2-. Which one can donate a hydrogen? The only thing with a hydrogen. And so it's going to be this first hydrogen that is donated over. Now, if it donates over, then I am going to make HCO3, and where I was 2-, now I've added a 1+, so the difference there is now I'm only 1-. Okay, and what do I have left over from my water? Hydroxide. And that is showing us that carbonate is actually a base, because what it's doing is producing hydroxide in solution. All right, let's label this. The hydrogen ion donator is our Bronsted Lowry acid. The hydrogen ion acceptor is our Bronsted Lowry base, like that. The entities, as they are separated by one hydrogen, are HOH and OH-. So I could link them, but first of all, let's just have a look at what happens when we reverse that reaction in some way. Okay, so say for example we remove some carbonate, our equilibrium will be caused to shift that way. Now, what can donate a hydrogen going backwards? Well, hydroxide is a polyatomic ion. It's very tightly held together, so that hydrogen doesn't really count. However, this hydrogen here is an acid hydrogen. It's on the front and can easily be popped back off again, like that. So that means that this guy here is the donator. So this would be my conjugate acid. This guy here is the acceptor in the reverse process, so he is my conjugate base. Okay? And then linking them together, the difference between entities with only one hydrogen between them, we have water and no hydroxide, and we have carbonate and hydrogen carbonate, like that. Okay? Good. Sometimes it is a little more difficult to determine what is going to act as a hydrogen donor and which is going to act as a hydrogen acceptor. Now remember, that's when we need our table from our data booklet, which is our relative strengths of acids and bases, and a simplified version of that, like this. On the top we have our strong acids, okay, and down here below the line is hydronium, and below here the acids get weaker and weaker and weaker until we get to the bottom where we have water in its own little category down there. So these are our weakest acids, like this. So if, for example, we had a situation with two, let's take HSO4-, and we're going to take HPPO4-. Now in this case, which one is going to act as the acid? They both have a hydrogen and they both have a negative charge. So if they both have a hydrogen, they could potentially act as an acid, and they both have a negative charge, meaning they could potentially both accept a hydrogen as well. So what I would do is look at their relative positions on the table, and the higher one up would act as our acid. In this case, the higher one up is HSO4 minus. HSO4 minus is here, whereas HPO4 is way down here. So that means that this is going to act as our acid. It's going to donate that way. And if it donates that way, then what do we have left here? We've got SO4 lost a positive charge to become 2 minus. And this guy gains a hydrogen to become H2PO4. Whoops, and he's 2 minus. I missed the 2 there, so make sure you note that. So when I add on another hydrogen, I become H2, and I reduce my negative charge to -1. Okay? Like that. So this one looks a little more weird because we have to choose which one is the acid. Whichever one is higher up will be, in this case, the Bronsted Lowry acid. Okay, so I'm just going to quickly label that Bronsted Lowry acid, Bronsted Lowry base, like that. Okay, and going backwards, the only one of these that could act as our conjugate acid would be the one with hydrogen. So this would be our conjugate acid, and SO4 would be our conjugate base. Linking together those entities, HSO4 goes with SO4 2 minus, the difference between them, just one hydrogen, and Bronsted Lowry base here, HPO4 2 minus, goes with the conjugate acid, H2PO4 minus. Okay? One more thing to note about those, so they're separated only by one hydrogen, but they're also always an acid on one side and a base on the other. Okay, so here we have acid and base. In the other pair we have base and acid. Okay, and that is the difference between them. All right, I'm going to leave that there for today, just a short video for us to remind us of what Bronsted Lowry acids and bases are all about, and we will continue on later. Bye for now.